In the previous lecture, we started to study Horseshoe Homology, as I remember, and we have defined the bar complex, bar resolution, bar of A, where A is K algebra, always K is always a commutative ring. Sometimes it will be a field. Well, bar n of A is simply 10th tensor power n plus 2th tensor power of A, where we write tensor instead of tensor over K, and of course tensor n plus 2 times is A tensor A, so on. N plus 2 copies of A. And the differential is defined by the equality if we apply it to 0 tensor, so tensor A n plus 2, we simply get the sum for I from 0 to n plus 1 minus 1 in the ith power, 0 tensor, so on, tensor. We glue A I and A I plus 1, and the rest is the same as before. So the number of tensors decreases by 1, and we get an element in the nth member. So as I remember, there is a map of complexes mu from bar dot of A to A, where A is, of course, a complex that has A in the 0 degree and zeros in all other degrees, defined by the equality. So as here we have only 0 degree, we have to define mu only in the 0 degree, so we have to define mu of A tensor B, and it's simply AB. So A tensor B is from bar 0 of A, which is A tensor A by definition. Well, so we have defined some complex. At this moment it's complex of K modules, and we have defined some map. So we want to show what first? First we want to show that this map is a quasi-isomorphism. After this we will so if mu is quasi-isomorphism, then bar dot is some resolution of A, but we don't know at this moment if it is projective or what, and so on. In general, it's not projective, but it is a relative projective, and what does this mean we will know a little later. So how to prove this? The proof is the same as in the case of bar resolution for groups. We simply define a map Sn from A tensor n plus 2 times to A tensor n plus 3 times, which is bar n of a, and this one is bar n plus 1 of a. And we define it by the formula Sn of 0 tensor n plus 1 is simply a0 tensor n plus 1 tensor 1. So we use that the algebra is unital, of course. For non-unital, mu is not quasi-isomorphism because it's not clear, for example, why this map mu is surjective. If A is unital, then we can take A equal 1 and get any element of A, yes. And if not, then it can be not surjective. Well, sorry, 1 moment. So now we need to check that Sn is a homotopy, which is called contracting homotopy for the complex A tensor A, so on. Where this part is bar and this simply a, yes, here mu. So we know that this is the cone of mu, may be shifted, and we know that to check that mu is quasi-isomorphism, we need to check that cone is acyclic. Well, of course, first thing that we had to check is that d and d n plus 1 is 0. And it is not very difficult to check because, like, we glue tensor in two places, and depending on the order of places, we get different sign, and so everything cancels. So it's exercise, and then to check that, then we get a complex here, because you can also check that mu d0 is 0. Yes, it's very easy. And what? And then we have to check that that Sn dn plus dn plus 1 is plus 1 is g. So we start is bar n plus 1 of A, and analogous equalities, but involving mu, that here we have to check that d0 is 0 plus s minus 1 mu. So here s minus 1 is well defined too, while here we will not have bar minus 1 of A, because bar minus 1 of A is not defined. We'll have here and here bar 0 of A, yes. This guy is d bar 0 of A, and mu s minus 1 is dA. Well, in fact, these two equalities are the same because of the same nature. This equality, because like mu is very similar to d minus 1. If we take this formula and write it for n equals minus 1, we will get the formula for mu. So it has another name only to highlight that d is differential and mu is not differential. It is of complexes, because this part is resolution and this part is A. Yes, and mu is quasi-isomorphism. So all of this is not very difficult to check, so it's exercise. Well, now let's understand that the bar out of A is a bimodule. A bimodule resolution of A. Well, because bar, well, A is A bimodule in the obvious way, because we can multiply A by elements of A on the left and on the right. And bar n of A is a bimodule via multiplication if you want to multiply by A on the left and by B on the right, we simply multiply the left tensor by A and the right tensor by B. So we get A0, tensor A1, tensor so on, tensor AN, tensor AN plus 1B. It's easy to check that it's a bimodule structure, and it's easy to check that dn bar out of A is a homomorphism of A bimodules so bar of A is a complex of bimodules and mu is a morphism of A bimodule complexes. Complex. All of this is not very difficult to check. If you multiply A by something on the left, AB is multiplied by the same thing on the left, and so on. So now a small remark on what is a bimodule. Yes, because if you have a ring R, yes, a bimodule over I is something that has left modular structure, right modular structure that are what's called compatible, in the sense that if you have a ring, then R bimodule is left and right module, R module M, such that R x s is equal to R x s for all x from M and R s from R. Yes, this you know. But when we talk about K-algebras, if A is a K-algebra, then A by module, considered as A by module over K-algebra, is not the same thing as A by module considered as A by module over A as a ring, because A by module is where A is K-algebra is the same thing as A by module M, where A we consider as a ring, such that alpha x is equal to x alpha for all x from M and alpha from K. Well, alpha here is the same thing, of course, as alpha times 1. Yes. Or in other words, what is algebra over K? Yes, algebra over K is a ring A with a homomorphism like it's called epsilon from K to A, such that the image of epsilon lies in the center of A. And if we consider this definition of K-algebra, then this guy is a homomorphism of unital rings. So it sends the unit of K to the unit of A. So it's the same thing as epsilon of alpha, yes. So always when we say A by module, we mean A by module where A is a K-algebra. So now a little portion of definitions. Well, A is a K-algebra. The opposite algebra of A is the algebra A op, which is equal to A as K module and has multiplication star defined by the equality A star B is equal to BA for all AB from A. So it's the same thing as algebra, as the initial algebra, but the multiplication in the opposite order. Probably you have heard about it, and you know that left modules over A is the same thing as right modules over A opened. Right modules over A is the same thing as left modules over A op. And also we define envelope in algebra. Of A is the algebra that is denoted by AE. It is A op tensor A. So if A is a K-algebra, then A op is a K-algebra, of course, where the map from K to A op is the same as the map from K to A, and AE is a K-algebra where the structure map epsilon sends alpha to alpha tensor 1 or 1 tensor alpha. It's the same thing because this tensor is over K. So why we need this algebra E is we need it because the category of A by modules is isomorphic to the category of A modules. Or sometimes people say that A by module is the same thing as AE module, in the sense that if you have M, just for example like A module, yes, then the bimodule structure. Well, if you have, for example, a bimodule, then we define the E module structure by the equality x times A tensor B is equal to AXB. And if M is an AE module, then we define A by module structure M A B is equal to X times A tensor B. So it's tautological. And of course we need this definition of A by modules, because here some scalar from K can be put to this side and to this side, because this tensor is our K. So here it has to doesn't have to depend where the scalar from K is. Well, it's not very difficult, but this allows us to consider the category of A by modules as the category of modules over some algebra, so we can apply all what we know about category of modules to the category of A by modules, and so on. Of course, if you consider A by modules as by modules our in, yes, where we consider A as our in, then here instead of AE where we have tensor over K, we would put Z, of course, like A by modules our ring A is the same thing as A tensor A op tensor over Z A modules. because scalars from Z always give the same result when we multiply by the left or by the right, on the left or on the right, because scalars from Z simply take the sum of copies. Well, so now our main definition. Let M be a bimodule which is the same thing as a module. Then the Horseshoe homology of A with coefficients in M is the homology of the complex C dot of AM, which is simply home over AE bar dot of A M. So we take the bar resolution of A, apply home over E to M, and get another complex. Then we take its homology, and it is Horseshoe homology. So nth Horseshoe homology is HHN of AM, which is HN T dot of AM. It's the same thing as HN home over AE bar dot of A. And the Horseshoe homology well, probably formally we need to put here minus n because of our convention about how complexes go. Horseshoe homology of A with coefficients in M is the homology of C dot of AM, which is bar dot of A tensor E M. So nth homology, nth Horseshoe homology is Hn of Am, which is Hn of C dot Am, which is the same thing as and homology of bar of A tensor E. Well, so let us now write more explicitly what is Horseshoe homology and homology. Yes, so Cn of Am is by definition Hom over A from a tensor n plus 2 times to M, and it's isomorphic to Hom over K from A tensor n times to M. Yes. So we have the complex C0 of Am, C1 of Am, so on. So it is here we have Hom over K from K to M. So we have here M. Here we have Hom over K to A from A to M. Then Hom over K from A tensor A to M, and so on. This, of course, Hom over K from K to M, yes. So, and here differential, like it is delta 0, delta 1, 2, and so on. So delta m is from, sorry, from Hom over K A tensor n to M to Hom over K A tensor n plus 1 to M. And if we look at the definition, then if you take f here, yes, and it goes to delta nf here, where then delta nf of A1 tensor an plus 1 is defined by the equality. First we take A1 f of A2 tensor, so on, tensor an plus 1. Then we take the sum for I from 1 to n minus 1 in the ith power f of a1 tensor so on tensor I plus 1 tensor so on tensor a n plus 1 and finally plus don't want to write on another board. So, okay, finally plus minus 1 in the n plus 1th power, and here f of a1 tensor so on tensor an plus 1. Sorry. Now, Horseshoe homology, a homology of complex Cn of an, which is by definition a tensor n plus 2 tensor over ae n, which is isomorphic to a tensor n tensor m. Yes, so now the differential goes in the direction that we convinced. So it's 0 of am, c1 of am, 2 of am, so on. And here we have as before m, yes, which is k tensor m. Here we have a tensor m, then a tensor m, and so on. Yes. So now differential Gn goes from a tensor n plus 1 times tensor m to a tensor m, and it is defined by the equality Gn of a1 tensor so tensor a n plus 1 tensor m is equal to what? First is a2 tensor so on tensor a n plus 1 tensor m tensor x a1 plus sum for I from 1 to n a1 tensor so on tensor ai plus 1 tensor a n plus 1 tensor x and plus minus 1 in the n plus 1th power a1 tensor so on tensor an tensor a plus 1x. Well, so we have defined the Horseshoe homology and homology, but at this moment we don't know what's the homological interpretation of them. So when we have defined group homology and homology, they by definition were some torus and x. And here, Horseshoe homology and homology, we want to be some x and torus too, but it's not exactly the same in general. So to interpret Horseshoe homology and homology as torus and x, we will need some more definitions from homological algebra. In fact, it's called relative homological algebra. So the next part is called relative extentor. So definition. Suppose that we have a homomorphism phi from S to R. Homomorphism of rings. Our rings are always unital, and homomorphisms are homomorphisms of unital rings. So now let M be be an R module. Then M is called phi projective. If the R module homomorphism pi from M tensor RS R to R defined by the to M defined by the usual equality pi of x tensor R is equal to xr splits. Splits is a homomorphism of R modules. Of course, because pi always splits as a homomorphism. Sorry, it's not clear what is split when we say homomorphism, so it's R module epimorphism, of course. Splits as an epimorphism of S modules. We simply can define sigma from M to M tensor over S R by the equality sigma of x is equal to x tensor 1. Yes. If we multiply x by something from S, then since this tensor is our S, it can be put to the right, and you will get the homomorphism condition. But if we multiply by something from R, it doesn't have to go to the right, so it's not a homomorphism of R modules usually. So now let's characterize five projective modules by a universal property. So suppose that we have, as before, homomorphism of rings. We have an R module. Then M is phi projective. If for any f from home our R from M to X to Y, and any G from whom our R from M from X to Y, such that G is an S-split epimorphism. There exists H from whom our R from X to X, such that F is equal to GH. So the picture is the following. As for projective modules, yes, you have M, you have Y, X. Here you have two homomorphism, our R, and this guy is epimorphism, and it is S-split. Then there exists a homomorphism our R here, such that this diagram commutes. The only additional condition is that this map has to be a split. So, for example, if S is a field, then we will get a definition of projective module course, any epimorphism, our field splits. Well, let us prove it. Yes. Proof. Well, from right to the left. It's easy, yes. We know that we have m tensor over SR to m, and it is a split epimorphism, as we have shown. And if we put here ID, then by the universal property, there is a R splitting here. So we are done. Let us now prove from left to the right. Well, so we have some x, some y, and here we have a split epi. Well, then we have m, and we have some map from to y, and also we have pi here. So if this guy is g, f, here we have f pi. First of all, let us prove that this module satisfies the universal condition. Yes. So how we prove this? Wait a minute. Yes. We have here some splitting, yes. So gamma is a homomorphism of S modules, not R modules, and we know that G gamma is equal to identical homomorphism Y. Yes. So we want to define first sum up here. Yes. How we define it? We define it. Let us be H tilde. H tilde of x tensor R is equal to. So first we apply pi, yes. Then we apply f. So it is f of x R. You get something here, gamma. So the question is why. Sorry. Sorry. This. So we have to check that this map is a homomorphism of R modules, that it is well defined, yes, and that it satisfies the required equality. So, well, G H tilde of X tensor R is, of course, G of gamma f of X R, but G is a morphism of R module, so it is G gamma f of X times R. G gamma is identity, so it is f of X R, and it is for f of X R, so it is f phi of X tensor R. Well, now we need to check that it is homomorphism of R modules, and it is clear because H tilde of X tensor RS is by definition gamma f of X RS, yes, and like it is gamma f of X R S, which is H tilde of X tensor R S. So it is homomorphism of R modules, and also it is well defined, because what we need to check to it to be well defined, we need to check that an element from S can go through tensor, yes, so H tilde of X tensor SR has to be equal to H tilde of X S tensor R for S from S, because these guys are equal. But this guy is what? It is gamma f of X is R, and this guy is gamma f of XS tensor R, but gamma and f are homomorphism of S modules, so we have gamma f of X is R, and they're equal. Well, so in particular, we have seen that M tensor over SR always is phi projective. So we have shown that it satisfies the universal condition, and we have already shown that universal condition implies phi projectivity, so everything is okay. And now, if there exists R splitting sigma from M to M tensor over S R for pi, then we can define H as H tilde sigma satisfies the required condition. It will be exercise. So we are done. In particular, we have shown that for any R module M, there exists a split epimorphism. This would be rho from P to M with P phi projective. We simply can take P equals to M tensor over SR and rho equals pi. And our proof implies that this module is phi projective. Well, now another definition. Suppose that we have, as usually, phi homomorphism of rings. We have R module. Then phi projective resolution of M is a complex zero, so on, here T0, T1 with quasi-isomorphism mu from P to M as usually, such that first Pi is phi projective for any I. Second, mu from P0 to M is a split, and like the map from P I plus 1 to the image of di is a split for any I more equal to 0. So if we add here M and write this long exact sequence as a composition of short exact sequences, all these short exact sequences have to be a split. Well, so our corollary that we have written here ensures that any R module has a phi projective resolution, and now we define relative pose indexed. Next phi n of m is by definition hn whom over R dot n, where and Tor phi n mn is by definition hn p dot tensor r n, where p dot is a phi projective resolution of M. So this and this are called relative X and relative Tor. Then what analogously to usual Tor and Ext, one can show that the definition does not depend on the choice of phi projective resolution, because we have universal property and we can show that two phi projective resolutions are homotopically equivalent and so on. And in fact, of course, this definition has interpretation in the terms of non-exact sequences that start at n and finish at m. We only need to choose non-exact sequences that split our S, and then everything will work. So the last remark is that if M has phi projective, and simultaneously aprojective, resolution, then next phi m is the same thing as Ext over R. And if it has phi projective R flat resolution, then phi n of m is the same thing as Tor over R. Well, it's clear because if you have some phi projective resolution, you calculate this and this using this resolution, and if at the same time this resolution is aprojective, you will calculate in fact Ext over R, and if it is R flat, then it will calculate Tor. So now how it is related to the Horseshoe homology and homology. So the theorem is that H n of A is Ext phi n of am and hn of am is store phi n of am where phi from k to I is the K algebra structure map. So it simply sends alpha to alpha tensor 1 or 1 tensor alpha. It's the same thing. First of all, we need to show that bar n is phi projective, yes? Yes. Bar n of A is by definition A tensor n plus 2. Yes, and as an AE module, it is simply A tensor n tensor A. Yes. So one second. So it is phi projective, yes. Model is phi projective. Well, yes, of course. Well, because if n more equal than 1, yes, then this is some R module, A module, and AE module, and we multiplied our K by AE, and it is phi projective. If n equals to 0, then it is AE, then it is R projective, but then it is phi projective too, because the universal property is satisfied. And also we know that Sn from the proof of our first lemma in this chapter lemma is a K module map so gives K splitting. Well, so we have shown that bar resolution is a phi projective resolution. And and as a corollary, if A is k-projective then HHN of AM is simply X out of the enveloping algebra, and if A is k-flat, then the Horseshoe homology is simply Tor of the enveloping algebra. And to show this, we simply need to show that that bar n is a projective or a flat, then but bar n of A, as we have shown, is A tensor over n tensor AE, and this guy is k-projective if A is, and it is k-flat if A is. And if we multiply our some k-projective module by A, we get our E by AE projective module, we get an AE projective module, and if we multiply some k-flat module, we get a k-flat module, because AE flat module, because this module is AE projective and AE flat. So in this case, bar n of A is AE projective. To show this, you simply note that A tensor n is direct amount of k in some power, then this tensor product is simply AE in some power. And here, bar n of A is AE flat. And here, to show this, you simply note that this tensor product is A tensor n tensor AE tensor dash, yes, this functor is isomorphic to the composition of functors. First you multiply our E dash, and then you multiply our k by A tensor n. But this module is AE flat, so this functor is exact. This module is k flat, so this functor is exact. And that's all.